You will be telling us about searching for de Sitter vacua in string theory.
Okay. All right, so I would like to first thank the organizers for the invitation to speak here. It has been a very nice conference. This is the title chosen for me by the organizers. A more accurate title is perhaps something along these lines. Just so you know that I'm not crazy, this is not what this talk is about. So the majority of this talk is an update on the search for de Sitter vacua in string theory. And this is a program that several of us have been pursuing in the past few years. The motivation is, of course, the observational evidence for an accelerating universe. Now, we find that very so often, one encounters tachyonic modes in a lot of these models that render the de Sitter solutions unstable. And we'll try to offer some explanations of why that's the case. Now, in the last 5 minutes or so, I will change gear a little bit and present an inflationary models that could potentially lead to detectable tensors on the CMB scales. And here you will see that tachyons play a much more welcoming role. As Joe nicely reviewed in his talk last week, it's rather challenging to construct a large field inflation model in string theory. So interestingly, we find that a tachyonic production of gauge fields induced by axion couplings in the early universe can potentially lead to detectable tensors at the level that we can see it in the foreseeable future. And I will try to argue that this scenario may have a natural home in string theory. So here is an outline of part one. I'll first review the case for the landscape. Then I'll go over several no-go theorems for de Sitter vacua in string theory and describe some attempts that we have made in constructing explicit models. Now, there's very little doubt that there is a landscape of string theory solutions, but many of them are expected to be not stable when supersymmetry is broken. And you will see how stability, or more precisely metastability, can impose a rather strong constraint on the landscape by just focusing on what we call the universal moduli subspace. So universal moduli here means that moduli that appear generically in a lot of string compactifications. And this is the content of the first paper. Then I would discuss the likelihood of finding de Sitter vacua, metastable de Sitter vacua in string theory, using some insights from random matrix theory. This part of the talk has some overlap with Liam's, and I will try to minimize the repetition. Okay. So first, the case for the landscape. As you all know very well, there are many perturbative formulations of string theory. And even if you restrict yourself to one of these formulations, there are many choices of compactifications with different topologies. And now, even if you fix the topology of your internal space, there are still many choices of fluxes. There are many ways of turning on these internal fluxes. Now, let's first focus on the flux landscape. If you have many moduli, there are many ways of turning on these fluxes. All these fluxes are quantized, and they contribute to the vacuum energy. So if you have many of them, you could have a very finely spaced discretum. Okay. Now, there are many contributions to the cosmological constant, quantum corrections. They all enter here. They could shift the vacuum energy up and down. But the key is that classical effects alone can already fill up the CC spectrum very densely. Okay. So that's the idea of the discretum. And the number of solutions grow quite rapidly with the number of moduli. If you have hundreds of moduli, then you have hundreds of solutions. So the question is, how many of this vacuum are actually stable? And would this picture modify when you take into account this issue of stability? Okay. So to answer these questions, we have to be a little bit more precise. Let's look at some explicit constructions. And in this talk, we will be focusing on the type 2 limits, where model building can be done a lot more explicitly, although it would be interesting to see how the story plays out in the other limits of string theory as well, such as the heterotic string. Okay. So in the type 2 limits, the most popular scenarios are perhaps the large form scenario or the KKLT constructions. judging from the number of talks being presented in this conference. The idea is to combine classical effects from fluxes with non-perturbative effects and sometimes perturbative effects or anti-branes to obtain a stabilized vacuum with a positive vacuum energy. And there are already many talks on this subject in this conference, and I don't have to go over the construction in any detail. This is a very nice idea, but in fine print, it's actually not so easy to construct an explicit model. First of all, the non-perturbative effects that are used to stabilize some of the moduli are very difficult to compute in full details. So most works on the subject aims to illustrate the existence of these instantons effects rather than computing the actual contributions, say by counting zero modes to make sure that the non-perturbable potential is there. But to compute the actual numbers that appears in the superpotential takes a lot more work. Furthermore, the full moduli dependence of this instanton effect is often suppressed. You can make some reasonable arguments, say a separation of scale. If you have moduli with very different masses, when you look at low energies, when at energy scales below the masses of this moduli, they can be treated as a constant, and so you don't have to worry about this complicated moduli dependence in the superpotential. But without making assumptions about separations of scale, you need to know the full functional form in order to say anything about the vacuum structure. Another point here is that these constructions oftentimes were discussed at the level of four-dimensional effective field theory, using four-dimensional concepts such as instanton generated superpotential. You can, of course, self-consistently demonstrate that a stabilized vacuum exists, but without making this a priori assumption, you ought to show that the candidate vacuum actually solved the full 10-dimensional equation of motions. And to do that is rather difficult because not only do you have to geometrize these instanton effects into a 10D language, you should find the back reactions of anything that you added to the constructions, such as the explicit Susy breaking source anti-branes. This proved to be rather challenging, and you will hear more about that in the next talk. So for our purpose of generating a sufficiently large sample space of solutions, of de Sitter solutions, and checking their stability, we will look at a different part of the landscape. Okay. In the type 2A limit, fluxes alone can stabilize all the geometrical moduli, although all the known examples so far were ADS vacua. Okay? So the goal of this sequence of work is to try to see how far we can go in getting de Sitter solutions in this context. Now, in this class of solutions, what we call classical de Sitter solutions, non-perturbative effects or explicit supersymmetry breaking sources are by constructions not included. And so the low energy effective actions can be computed rather explicitly within supergravity. Now, as you will see, these classical de Sitter solutions in fact solve the full 10-dimensional equation of motions and are not just critical points of a 4-dimensional effective field theory. And because they are so simple, they can be easy. One can carry out rather easily systematic statistical studies, which we will say something about it midway through the talk. Okay, so in this context, what are the ingredients that we have? Well, the ingredients at our disposal are the fluxes, branes, which include d-branes and orientable planes, and the curvature of the internal space. Okay? So each of these ingredients give competing contributions to the 4D vacuum energy and competing forces on the moduli. Okay? So for instance, the fluxes contribute positively to the vacuum energy, and they tend to make the internal space expand in the limit when the flux density is diluted. It's an energetically favorable configuration. And d-branes, on the other hand, tend to shrink the submanifolds on which they wrap. Now, the curvature of the internal space can contribute to the vacuum energy, and it can come in either sign. Depending on whether the internal space has positive or negative curvature, it could have a positive or negative contributions to the 4D energy. Okay. So in this context, finding de Sitter solutions amounts to finding a balance between these several competing ingredients. Okay. Now, if we want to stabilize moduli, we have to know what they are. And in general, this is a model-dependent question. But there are at least two moduli that appears generically in any string compactifications. They are the dilaton, which I call tau, and rho, the breathing mode, which controls the overall size of the internal space. Now you can ask, what do fluxes, deep branes, and curvature do? They all contribute to the vacuum energy in some way. And it's very easy to figure out how they contribute to the potential in terms of this moduli. So very simple argument will tell you how they scale with this universal moduli rho and tau. And also the contributions come with a definite sign. If you know what ingredients you have, you know whether the contribution is positive or negative. Okay. So it turns out, simply from this scaling, you can already prove many useful no-go theorem for de Sitter vacuum in string theory by finding inequalities of this form. Okay? So suppose you manage to find an inequality that involves a derivative of the potential, like the left-hand side, bigger than a number, positive number times the potential. You can show that at a critical point, the vacuum energy cannot be positive. Okay? So simply from the scaling, you can already say a lot. In fact, this excludes the possibility of getting this class of classical de Sitter vacuum in a class of promising models, intersecting brane models. Okay? So because in this class of models, the type of ingredients that we have is very specific. We have a Calabi-Yau space. We have intersecting sex branes. We know how all these ingredients give you, how the potential depends on these ingredients. Just from the scaling, you can show, as was done by this author, that you cannot get a simple de Sitter vacuum in this context. Okay. Of course, this does not mean that these intersecting brane models cannot be made consistent with cosmology. It just means that the ingredients that you need to introduce should be more complex. You need to put in instantons. You have to maybe turn on additional fluxes and more branes, and so on. Okay. So this no-go theorem concerns only with the existence of a de Sitter critical point, not necessarily a de Sitter vacuum. Okay. So now this is where the complication comes in, because now you would have to show that the full mass matrix at the critical points have only positive eigenvalue for stability. And if you have an explicit model, you can of course go about and check it. It's very time consuming, and furthermore, it can only be done in a case-by-case basis. Okay. Different models, you have to diagonalize a different size of the matrix. But it turns out, interestingly, we show that you can still impose some very powerful constraints on the stability of this de Sitter extremum by just looking at the universal moduli subspace. So the absence of tachyons necessarily require the determinant and the trace of this 2x2 submatrix to be positive. If any submatrices of the full Hessian matrix has any negative eigenvalue, the full mass matrix cannot be positive definite. And turns out this simple criteria is constraining enough to rule out even a lot more models. Okay. Of course, any no-go theorems come with some assumptions, and you can there are certain ways to evade them. One assumption you can relax is the Ricci flatness of the internal space. So intuitively, you can understand why this might help, because a negatively curved internal space contribute positively to the 4D energy. This is the reverse of ADS5 cross S5 type of Freud-Rubin compactification. In that case, it's a positive curvature that makes the external space negatively curved. Now, this looks promising because many classical ADS vacuum were known to arise in flux compactification. And so to construct de Sitter vacuum, we are led to make some extension and consider reductions on internal spaces that are negatively curved and in the presence of a variety of fluxes. Okay. So this brings us to the next subject. Interestingly, these extensions were considered before in the context of generalized complex geometries. And among these non-Calabi-Yau compactifications, many of them are negatively curved, at least in some regions of the moduli space. So many attempts have been made to construct explicit de Sitter vacuum, and I will try to summarize the status of this search. Okay. So the strategy that we would take is to take some of this known ADS vacuum. Okay. So we know what kind of ansatz for the fluxes would give us ADS vacuum, and we can try to modify and improve the ansatz for the fluxes and look for de Sitter solutions. Okay. So one point which is important to make here is that we are looking for spontaneous supersymmetry breaking state in the supergravity. In particular, the supersymmetry breaking scale that for the models that we're looking for are below the Kaluza-Klein scale. So we can therefore compare our results with similar searches for de Sitter vacuum within supergravity. Okay? So let's say consider SU3 structure manifold. Okay? So there are more general supersymmetric backgrounds that could that does not have to be necessarily Ricci flat. And SU3 structure manifolds are more general supersymmetric backgrounds where the globally well-defined spinor is not necessarily covariant constant. And so these two forms, J and the three form omega, are not necessarily closed. And there's a lot of beautiful mathematics that go into this subject. But what is relevant for us in the search for de Sitter vacuum is that there exists rather explicit expression for the Ricci tensor for this SU3 structure manifold in terms of these universal forms. The two form J, the three form omega, and distortion forms that sort of define this SU3 structure manifolds. So even though we know a lot less about this type of constructions, we can still solve the equation of motion rather efficiently. Okay? So if the Ricci tensor can be expressed in terms of this universal form, so is the energy momentum tensor. Okay? So it's natural to consider the following ansatz for the fluxes, which depends only on these universal forms. Okay? Now, the universal forms J, the torsion forms, and omega appears in all SU3 structure manifolds. So this ansatz therefore allow us to scan a large class of models without knowing too much about the details. Okay? So there's one more simplification that we are going to make, namely we are going to consider the approximation of smear-orientable planes. Okay? And meaning that we spread the charge and the tension of the O planes over the internal space. This is of course not the actual situation. A more precise treatment is to not make this simplification and search for the back reactor and solve for the back reactions of these O planes. Now, as you know, finding back reactor solutions of localized sources in supergravity can be a tough business. And you can think of smearing the orientable planes that we have done here as solving the equation of motions in an average sense. Okay? So instead of solving the full set of equations, you only solve the integrate version of this equation of motion. But it's a good starting point. Now, because of the simplicity of the ansatz, namely everything depends on the universal forms, you can express all the equation of motions and the Bianchi identities in terms of very simple algebraic equations instead of differential equations. And I will skip over the details. Okay? So what we find is that while ADS vector are abundant, de Sitter solutions are a lot harder to come by. And instead of going into the details, this picture sort of illustrates what you typically find. So here, the x-axis that I'm plotting here is the ratio of some fluxes. Okay? So you can think of it as some slices of the parameter space. And as you can see, physical solutions exist only for a range of parameters. Okay? These guys have to be positive definite, so you cannot turn on arbitrary fluxes to get physical solutions. And within this range of parameters, only a tiny window allows for de Sitter solutions that are stable in the universal directions, namely the rho tau direction. Okay. Now, just to recap, what we have done up to this point is to find a set of necessary conditions on the fluxes and the torsion classes in order to construct classical de Sitter solutions. Okay. This is a useful first step, but there's no guarantee that you can find explicit models, explicit geometries that realize the conditions that we find. Okay. But fortunately, if you look more closely, you find that there are examples. So it turns out the necessary conditions that we find, that I skip over here, can indeed be realized in some explicit group manifolds. Okay. So for instance, an SU2 cross SU2 group manifold, in some region of the Morgei space, they can be negatively curved, and it looks like it satisfies all the, it evades all the no-go theorem that we know. But when you look at the mass matrix of these group manifolds, you find that among the light modes, at least one of these directions is tachyonic at a critical point. Okay. Now, for homogeneous spaces such as group manifold and coset spaces, you can construct explicitly the SU3 structure. And because the model is so precise, you can check not only for critical points, but also the fluctuations around the candidate extremum. And you find that in this model there are 14 like modes, and among them at least one of them, 10 minutes. Among them, only one of them is, at least one of them is tachyonic. Okay? And so I have to speed up a little bit because I really want to tell you about the work towards the end. So this motivated us to carry out systematic search, and our search covered all the 6-dimensional group manifolds, although it's rather easy to extend it to coset spaces as well. And instead of showing you the constructions, let me just give you the punchline. We find that there are about 50 group manifolds that we know in 6 dimensions that can be made compact. Among them, only a handful of them have de Sitter critical points that are consistent with the orientable symmetries. And each of these group manifolds are like the one I showed you. There are about 10 like degrees of like modes. And Gauss's law constraint limit the flux quanta to be something of order 10. And so you would expect that would be a sample space of about 10 to the 10 solutions. And our systematic search gave several de Sitter solutions, but all of them have tachyons. Okay? Of course, we don't have to study all of these 10 to the 10 solutions in any detail because many of them do not make the cut in the first pass. For instance, the equation of motion, the fluxes that satisfy the equation of motion denoted by the blobs here are not necessarily properly quantized, and even if so, they may fall outside the supergravity regime. Now, our systematic search for de Sitter vacua turned out empty. Is there a way to understand this now result statistically? So this is the content of the second part. Now, since there would be a similar discussion in Liam's talk, I think I can short circuit some of these things. Over here, first let's make a very simple estimate for the probability of an extremum to be a minimum, and consider a very simple toy model for the landscape. Suppose you can write down the potential on the landscape, a multidimensional potential, as a sum of many one-dimensional potentials. Okay. This is an assumption. And this argument was due to Susskind and was implicitly assuming the Booster-Polchinski argument. Okay. So now if each of these one-dimensional potential has to an extremum, it's reasonable to expect that roughly half of them are minimum. So if you have n fields, the total number of vacua, it will be n to the n. The probability for an extremum to be a minimum is very small. It's 1/2 to the number of fields. It's exponentially small, but still the number of vacua can be exponentially large if your potential has enough extremum to begin. However, we are interested in de Sitter vacua, not just any minimum. This argument makes no reference to the vacuum energy. And furthermore, the various fields, they interact with each other. It's not a factorizable potential. It's not so simple. And in particular, when you look at this type 2A flux vacua, the potential receive field-dependent F and D terms. So the moduli are highly mixed. So in these situations, you cannot use this argument to estimate the number of minima. And if you want to check the Hessian mass matrix is positive definite, it's going to be very difficult. Fortunately, if you're only interested in statistical questions, like what happened to a large ensemble of matrices, complicated matrices, random matrix theory should give you a rather reasonable estimate. Okay? So, so the type of result that we would need is questions like this. Given a randomized matrix, what is the probability of drawing a positive definite matrix from an ensemble? And the key phenomena that you sort of would have guessed is eigenvalue repulsion. If you have a large enough matrix, the probability of finding all the eigenvalues to be positive is very small. And in fact, you will see that the probability is Gaussianly suppressed. It goes even faster than exponential. So if your number of vacua is only exponentially large, it's unlikely to find metastable vacua. And since, how much time do I have?
6 minutes.
6 minutes? Okay, I think I can go through this rather quickly, and it wouldn't hurt to hear it the second time. When we talk about random matrices, we have to specify an ensemble, and one of the simplest and best known example of an ensemble of random matrices is the Wigner ensemble. Elements of this ensemble are matrices of this form, and you know a lot of results about these random matrices at large n. At large n, the eigenvalue spectrum of a Wigner matrix converge to a semicircle, where rho of lambda here is the eigenvalue density. Okay? So this gives you the typical configurations of eigenvalue. It doesn't mean that you cannot find eigenvalues in this. You cannot find matrices in this ensemble with eigenvalues outside this range. In fact, this semicircle has a soft edge. There's a non-zero probability for one or several of these eigenvalues to be found outside this semicircle. Okay? But we are not interested in small fluctuations. We are interested in large fluctuations through which all the eigenvalues are pushed to positive values. So we compute this probability for one of these ensembles called Gaussian orthogonal ensemble, which is a collection of n by n matrices with, which are real and symmetric. And to do that, we consider an ansatz for the probability of this form, which seems to work very well with our simulations. And our results also quickly converge to the large and analytic results, not only in its form, but also the prefactor and the subleading corrections. Now, we find that for a sufficiently large matrix, say n of order 10, the probability is easily Gaussianly suppressed, although our ansatz seems to work quite well for small n as well. Now, this is something that Liam will tell you more about. So what we have assumed here is that the Hessian is a randomized matrix. If you're looking at a model that descends from a supergravity, you could randomize the superpotential and its covariant derivative instead. And I'll skip over this part and let Liam tell you more about it. Instead, let me just quickly address how uplifting can affect the stability of vacua. Okay? So we can model this problem as a sum of two matrices. One is a mass matrix corresponds to the Hessian at an ADS minimum, and the other is the uplift contributions. Okay? So in principle, the mass matrix and the ADS minimum is not necessarily positive definite, as we know that negative mass square does not necessarily signal instability in ADS space. But to play it safe, we start from an ADS minimum whose mass matrix is positive definite and diagonal. Okay? And then we can ask how much uplifting contributions to the potential can we add before the probability turns Gaussian. Okay? So turns out the ansatz that we took works pretty well in this case as well, even though the mass matrix is not necessarily completely random. There's some hierarchy between the diagonal and the off-diagonal terms, except that the coefficients that appear in the ansatz are now functions of the uplift. And we see that for a mass matrix of order 10, the probability turns Gaussian very quickly, even for a moderate amount of uplift. So from this work, we can draw some general lessons about the landscape. As you have seen, as we lift the cosmological constant, the off-diagonal terms of this Hessian matrix become bigger, and the extremum becomes unstable. So raising the cosmological constant has the effect of destabilizing the classically stable vacua. And you can try to improve the chances of stability by looking for models that have a hierarchy of masses. For example, if the number of critical points is controlled by the total number of moduli, whereas the fraction of this critical points being stable is controlled by the light modes, the potential. And if there's a large hierarchy between these two numbers, you can try to beat one with the other. Okay? But as you go to higher and higher energies, more and more moduli come into play. There's no clear distinction between the heavy mode and the light modes anymore, and so you expect the probability to be more Gaussianly suppressed. So let's go back to this picture. Perhaps the landscape, after taking into account the stability, may look somewhat different. In counting the 10 to the 500 vacua, each of these critical points was given an equal weight. But as we have seen, the probability for any of these solutions to be a minimum depends highly on the vacuum energy. Okay. Do I have a few minutes? Okay, 1 minute. That should be enough. Okay. So in the remaining time, I will talk about another role of tachyons in string phenomenology. Okay. I will present a simple inflationary model where detectable gravity waves on the CMB scale can be generated by a tachyonic production of gauge field induced by axion couplings. Okay? So as you know, it's quite challenging to construct controllable inflationary models with large tensors. And the current observational the observational limit of the tensor to scalar ratio, which is usually denoted by R, for some ongoing and forthcoming experiments is roughly of the order of 0.01. And a very simple argument due to life suggests that a trans-Planckian field range is needed. And so you typically lose controls of the effective field theory. Okay? So scenarios which effectively increase the effective field range have been suggested. And I will not say anything about these scenarios. I refer you to Joe's talk for a discussion of the issues. But here I will present a rather simple model which can generate gravity waves, detectable gravity waves, even for small field inflation. And the idea is particle production in a time-dependent background. So suppose in addition to the infraton, you have a hidden sector consisting of an axion and a gauge field that couples to the axion through this axion coupling. But as a whole, this sector is coupled to the infraton only gravitationally. And the time dependence of the axion can lead to particle production. And a very simple argument, a very simple calculation shows that one helicity of this vector modes get copiously produced because the axion coupling induces an effective tachyon mass for the gauge fields, whereas the production of the other helicity mode is suppressed. Okay. Now, the particle produced source gravity waves, but it also contributes to the scalar spectrum. So the question is whether the effect is big enough on gravitational wave measurements and not screw up the scalar perturbation. Since Stuart didn't give me time to talk about it, I will just show you some plots. Okay, so we have calculated the effect on the tensor spectrum and the scalar spectrum and non-Gaussianity. And here are some plots. So you see that a detectable tensor mode can be consistent with current observational bound, and this is this shows the tensor mode as a function of different slow roll parameters. And for models that give detectable tensors, the axion constant fall within this window, which seems pretty reasonable. Okay. Now, one distinctive features of this model is that the gravity wave, different helicities of the gravity waves are produced with different amplitudes. And just like in particle physics, you can define a forward-backward asymmetry. Here we can define a parameter that measures the handiness of the gravity wave signal. Okay. Now you can see this is the handiness as a function of R. You can see that some of the ongoing and forthcoming experiments can already potentially detect this kind of parity violation. Okay. So P here is Planck as a spider, and the sensitivity of some future experiments such as the MP-PO would really be able to nail this model down. Okay. So there are many axions in string theory, and with decay constant typically of the order of a gut scale. So this seems to fit very comfortably within the window of our model. And the pseudo-scalar coupling comes from the Chern-Simon coupling to the UN gauge field on the D-branes. It's not so difficult to find candidates for the infraton that couple only gravitationally to this hidden sector. And in this model, a detection of gravity waves probes not the scale of inflation, but rather the nature and dynamics of axions, which is perhaps equally exciting. Okay? So let me just end with this positive note. Thank you.
Any questions? Yeah.
Hi, Gary. Yeah. So in a previous version of this argument with the gauge fields, I was remembering that before you produce large gravity waves, you actually produce no Gaussianity from the inverse decay of the gauge fields to the
So the non-Gaussianity bound is right here.
But what's different to those previous?
So the previous model is not a hidden sector. So actually the axion could be the infraton. So here we have, in addition to the infraton, some axion that coupled to the gauge field. Previous models were basically axion being the infraton and coupled to the gauge fields. And there are stronger bounds on the scalar spectrum because the perturbation was generated by the axion itself. Here, within a reasonable range of parameters, you can show that the back reaction on the scalar spectrum is very small. And as long as some of these constraints are satisfied. So that's the difference. And it's also not so unreasonable to expect, in addition to the infraton, you have some axions because of shift symmetries.
In your search of the Sitter vector, what controls the curvature of the space? The Sitter is an independent parameter that you can tune. It depends on fluxes. But is it of the order of the string scale?
So they are similar to, but they are geometric fluxes. right? So they are quantized so that if you they are not too different from the string scale, you can tune power laws like dependence. You can make it somewhat smaller than the string scale, but it's not exponential.
The quantization. The question is the quantization turns the vacuum energies to be larger or less than the string scale.
They are below the string scale. The contributions to the energies.
In other words, it's not linear. It's not linear. The dependence of vacuum energy is not linear in the fluxes.
It depends also on the moduli, right? So the moduli can take bigger than string scale value to make the contribution small.
Yeah, I don't understand. If you have no parameter that controls even discrete parameter that controls the vacuum energy, then what is the difference? Try to find the Sitter vacuum by just non-supersymmetric solution. Any non-supersymmetric solution will generate a cosmological constant that could be either positive or negative.
So these are not KK scale Susy breaking. This vacuum break supersymmetry at a scale below the KK scale. So there's a parametric separation of the scale here.
Okay, so I have 3 more questions. Quick questions.
Have you checked to what extent the tachyons arising in your group manifold reductions, whether they coincide with these Goldsteiny, and if they do, to what extent that just the instability already arises from the Skruka bound?
So they are not the they are not the Goldsteiny.
They're not identical, or they're not aligned at all?
No.
They're orthogonal to it.
Yeah.
Wow.
You discussed how to define the Sitter vacuum and making out the instability. I was wondering how you can finish this inflationary phase and if it is related to such an instability.
So I was not talking about inflation at all. So the first part of the talk is a basic question about whether you can get the Sitter vacuum. So of course you can make similar statement like what was made here for inflation as well. It was done, but inflation is the second step.
The estimate you had for the number of vacua that survive seems to be the most pessimistic scenario where the matrices are truly random. If the trace has a large expectation value for some reason, then you can suppress the number of negative eigenvalues substantially. Do you understand why the trace might be 0 or no?
No. The trace does not have to be 0. So in fact, the plots sort of answer your question. So we're asked, you can have a large mass matrix, very diagonal large value. You can add a bit of uplift to the potential and see how much uplift you can do to screw up the stability. So if you wish, the trace is not 0 to begin, and then you add this small addition. Turns out a very small amount of uplift can already make the probability Gaussian. So this is like 2% addition. You can compare the variance of the two set of random matrices, and a small amount of uplift can lead to suppression.
Okay, let's thank the speaker again.